Forces in two dimensions. By the end of this lesson, we'll be able to describe the interactions in multiple dimensions and use components correctly to calculate forces from a force diagram while keeping our components off of a free body diagram. A modified Atwood's machine is an apparatus composed of an ideal string and pulley where at least one mass is hanging while the other mass is on a flat surface or placed on an inclined plane. An inclined plane is a simple machine that consists of a plane that is placed at some angle to the horizontal plane. Let's look at a box on a rough inclined plane, or ramp, or hill, or mountain, or whatever. It's just a right triangle when we look at it with our usual coordinate system that is tilted some angle theta above the horizon. The situation can be solved using forces most of the time. So we'll start with the easy one. Weight force going down. The normal force is normal to the inclined plane. Because the surface is rough, there is a frictional force which opposes sliding, so the frictional force is directed up the hill. Let's free the body here. Now we have multiple vectors at an angle, so we would need to resolve multiple vectors into components. But there is a shortcut. If we lay the coordinate plane along the inclined plane like this, this allows us to analyze the forces that are parallel to the ramp and perpendicular to the ramp rather than horizontal and vertical. Now there's only one force that does not fit the description of parallel and perpendicular, and that is the weight force. So we must resolve the weight force into components that are parallel and perpendicular. By far the most difficult part of this process is drawing the correct triangle. Follow these steps and you won't have to worry about that. First, we'll continue the normal force into the inclined plane like I did with the blue dotted line there. Next, we're going to connect that dotted line to the weight force. Just like that. So we start with the normal force being continued into the inclined plane, and then we connect that to the full weight vector. Remember that components of forces do not go on a free body diagram that's showing all of the forces acting. Instead, they only go on free body diagrams that are being used for problem solving. Only now we have a right triangle and we draw it like this, so the angle between the perpendicular component of the weight force and the full weight force is the same angle that the inclined plane is relative to the horizontal plane. So we started with that angle theta. That angle theta is that same angle. This makes the parallel component of the weight force mg sine theta and the perpendicular component mg cosine theta. Now we can use Newton's second law to analyze the forces perpendicular and parallel to the ramp. For the parallel direction, we can see the weight force is not what makes it go. Instead, just a small piece of the weight force does, while friction resists the sliding. If this were a smooth ramp, there would be no friction, and we would have mg sine theta equals ma. Or, if the problem states there is only static friction but no kinetic friction, there's still not going to be any friction on your free body diagram for a box. If it's a wheel, that's a whole different story. We'll come back to the parallel direction in a second, but first let's look at the forces that are perpendicular to the inclined plane. So the forces perpendicular are the normal force minus mg cosine theta. And because this box is not sinking into the ramp, and it's not being ejected upwards, we should be able to see the perpendicular forces are in equilibrium, which means there's no acceleration, so our normal force equals mg cosine theta. This is important because the frictional force relies on the normal force. Remember, frictional force equals mu times the normal force. So we get mu times mg cosine theta for our frictional force. Our forces are in equilibrium in the parallel direction as well, so there's no acceleration in the parallel direction for this situation. Let's say we want to solve for the coefficient of kinetic friction. Divide mg cosine theta from each side. Cancels out. On the right side, on the left side, mg cancels out, and what we're left with is mu k equals sine theta over cosine theta. That equals tan theta. And so one trig identity it's going to be useful to know. This is true for any object that's on an inclined plane that is not moving. So if you want to remember the coefficient of static friction for an object that is not moving on an inclined plane is equal to tan theta, you can do that. Have at it. Let's back up a little bit. Let's say we had no friction. Then we have stuff that makes it go, mg sine theta equals mass times acceleration, and we can divide each side by mass and see that acceleration down the inclined plane equals g sine theta. That's true every time there's no friction on the ramp. If the object is sliding and there is friction, there's our frictional force. Let's solve for mu again this time. From here you can simplify. Just remember there's no g term in the MA. So what we're left over with is mu k equals g sine theta minus a all over g times cosine theta. I would leave it right there unless there are numbers involved which you can plug in. Now let's look at a critical angle. A box of mass m is placed at rest on a ramp. The coefficients of static and kinetic friction are mu s and mu k. As the ramp is slowly raised from the horizontal orientation, find the critical angle above which the box starts to slide. Very common problem. This is a force situation. We're talking about friction. So we would start with a free body diagram. From the free body diagram, stuff that makes it go minus stuff that holds it back equals mass times acceleration. Because there's an inclined plane, we resolve the weight force into vectors by continuing the normal force into the ramp and then connecting that continued normal force into the ramp to the full weight force. The angle of the inclined plane is the same angle between the perpendicular component of your weight force and the full weight force. So stuff that makes it go minus stuff holds it back equals mass times acceleration. If the box has not begun to slide, that means our acceleration equals 0. So mg sine theta, the stuff that makes it go, minus our frictional force, mu times Fn. Remember that Fn equals mg cosine theta for this situation. So we have mg sine theta equals mu times Fn, which is mg cosine theta. So the process is exactly the same. We get here, right, mu s equals tan theta. Now we want theta all by itself rather than mu. So we would take the arctangent of mu to get theta. Next steps, you can never solve too many of these types of problems. For more practice, there's your AI. Ask each other, ask me, keep asking until you get it.